And it looks like we're live. Welcome back. Today, I'm going to continue looking at the rlpx transport protocol for Ethereum. I did a bit more Googling and playing around, and the way it works is dev P2P. This dev P2P concept is the peer-to-peer networking protocols used by Ethereum. It's used by all the clients, especially two big ones, and they'd all have their own implementations. A sub-protocol of this dev P2P thing is rlpx, and also the discovery. So the discovery protocol defines a heap of ways. It's like their equivalent of an IP address. So they've got a cryptographic identity that's based on the distance between two nodes. So the closer nodes, I believe, are close in terms of like cryptographic distance between the two nodes numbers. So when you've got your node, you have your address, another node has an address, and there's a distance between them, which is just the XOR, exclusive OR of both of them. And then this distance they use to determine who to send to, because the closest nodes are is this distance, and it just says that I think it's you send information only to the closest X amount, and that way everyone who's sending stuff around a network eventually gets everyone without having to send it to everyone. I'm not going to dig into too much of this right now, but that is when we're looking at this P2P in here. There's the Discover v5. This is talking about v4, but there's a newer version now that's not updated on this wiki. So we'll dive into that at some point. But the point is that when you connect to a network, you start with the first hard-coded nodes that are in your Ethereum Geth chain. I wonder if we can find that quickly. See, discover VM table. Yeah. The topic discovery protocol provides a way to find nodes that can be connected to. Yeah, not in there. Clear. Database. VM table test. The other place it might be, and if it's not, I'm not going to dig into it too much. Params. Yeah. Maybe protocol network. Nope. VM proto. No, boot nodes. There it is. Cool. So in this params, they got these E nodes, and they got the cryptographic hash of something, I don't know what yet, at IP address port. And at 30303, is just the port number for these if rlpx. Somewhere here it says the default's 3030. Cool. So the rlpx sends messages. Messages is what we were looking at yesterday. We dove in a little bit in the wrong direction and end up looking at what the messages talk between channels and Go routines. But this rlpx defines a way to talk between two nodes. The key here is it has nothing to do with Ethereum yet, because you can define sub-protocols in this you define sub-protocols as part of this dev P2P, and examples of the sub-protocols are the Ethereum wire protocol. Another example is Whisper and Swarm. Whisper is also in here, Whisper, and here's Swarm as well. And they're unrelated to blockchain stuff, but they use the same protocol for peer-to-peer communication to do. In here, Whisper is messaging, and Swarm is file saving, I believe. I haven't dug into them too much. They'll be on the list after everything else. So the peer-to-peer network is exactly like a torrent network. You have peers on it, and for example, a sub protocol for rlpx might be another torrent, or they've defined this Ethereum wire protocol, and that's where you sync the chains and all that fun stuff that actually has to do with sending transactions. Now, if you look in here again, there is the ETH subdirectory here, and in here is the stuff that relates to this Ethereum wire protocol. Gonna get to that, but today I'm gonna go a bit further into this rlpx, and this is quite a decent sized file, and it's pretty heavy too, in terms of code difficulty and abstraction. So what happens is a lot of this protocol doesn't care what the messages that are being sent. They take that generic message file structure, which is really just a code and a byte array, and it's saying it should be rlpx, not rlp, it should be recursive length prefix, but that's the structure of the binary, the way it's saved. And something that I read today, which kind of is interesting, is the reason rlp for saving binary structures is used is because it's actually smaller than JSON or any other really way of saving data structures. If you save it as XML or something, it's got a huge amount of overhead. If you save it as JSON, it's got a little bit, still human readable. This one, rlp, doesn't have very much at all, but it's probably less human readable. We haven't looked into it yet, but on the list, probably coming up quickly, because it keeps coming up, and it seems to be like a core concept of Ethereum, really. So not looking into the wire protocol yet, but the lower level transport protocol dedicates a lot to this cryptographic handshake. So if you've got a website, most of them these days use TLS to make sure everything that's sent between the client and the server is encrypted. If you're sending a password as a login, you definitely want it secured by TLS. And the way it kind of works is, it's almost typical how you would speak in code, just formalized into like a computer protocol. Really, it's you would meet someone, you establish a secret key that's used in encrypting your codes, and then whenever you go forward, if you were a spy or something, you'd write your messages and you would code them using that key. And then in TLS, that's exactly what they do. There's a formal, the node reaches out to the server, says, hey, look, I want to connect to you. This isn't encrypted. They send, no worries, here's my information. Send everything encrypted over that for a little bit. So they encrypt it using the public key that's available there. Because it's public, it doesn't matter if anyone sees it. Then they send back a different public key, and using the two public keys and encrypting a few messages between them, they establish a secret that even if someone is listening to it on the outside, the whole message, they cannot determine what it is. And that's to do with the Diffie-Hellman exchange. That's quite a key concept in use in all cryptography, and it's one of those things that because this exists, we can have secure internet. Yeah, it's quite beautiful. Alice and Bob are talking. You know, they've got some secret colors. They mix them. As a result, they have a common secret. Anyone who's listening to all the communications can't figure it out. There's quite a lot of good YouTube videos on that. Recommend reading that if you have some spare time and would like to waste a bit of time learning about cryptography. So this is exactly what this transport protocol does. Yeah, they don't use SHA, which I think is Diffie-Hellman. They use elliptic curves again. The handshake is the first time you meet, you send a handshake authentication message. And that authentication message is the encrypted, the public key, the secret, the shared secret. And I don't really want to dig too much into this, because the concept is that they do all this stuff so that they can communicate between each other secretly. And they have this shared secret, which is just a number that is used to encode everything that goes between them. So they do a handshake. They create this shared secret. They send messages going forward that are now encrypted. And also, a key part of this rlpx transport protocol is that they have signatures, the egress, which is outwards, ingress, which is inwards. And I'm not fully sure the head around it yet, but every time a message is sent, either received or sent, the MACs are updated using the previous stuff, and it's just so you can keep track of the messages that have been sent. If stuff gets lost, then this will not be up to date. So in here, in its rlpx, an ungodly amount of effort is spent on making it, like the whole thing surrounds by this handshake and making them secret. We start with this rlpx structure, which really just wraps an rlpx frame. This connection is also included in this, and there's a mutex to say you can write to it or not, and that's just to give it thread safety. And then this read message really just goes passes it down to this rlpx frame read write. And I was looking at this yesterday, didn't fully understand it yesterday. I've looked into it a bit more, so it's kind of got my head around it a little bit more. Hopefully going through these details today will clarify it all for myself and everyone watching, really. So this overline structure, rlpx, passes any read message, write message down to this lower frame. It's just wrapping it. So when you create this, you pass it a connection. So you made a connection with someone somehow. If you're running a node, it's got a server listening to people who are talking to you, and you've also got the option to dial to some people who are in your node list. So you've made a connection with someone who's a node. You're going to send them this stuff. You're going to begin discussing some Ethereum via the rlpx transport network, transport protocol network. So all you do is you pass this connection, and then you're going to do stuff with it. Setting some deadlines. I don't really want to look into that too much, but I imagine it's exactly what the name says, and it's that net golang set deadline. I imagine it's just you set it as like a timeout. What's the purpose of deadline? From the name, I guess it sets a deadline on now. Refers to the net in dial.go. It returns the first deadline to come between that and a timeout. So it just times out the connection. So they're giving a way to time out the connection here. Here is some stuff to close it down. You've opened a connection with someone. You close it when you're done with it. As you're disconnecting, you might get some errors. Disconnection reason to the disconnected peer. Cool. So here is where they go into the deep handshake. I imagine this is the first one, the do protocol handshake. And it's got a protocol handshake structure being passed to it. There's a handshake message being sent down the channel for read write for errors, W error. We prefer returning handshake read error. If the read error is 0, I guess it's a positive. So what's handshake? Handshake message. I imagine it's up the top. Nope. Where is that defined? So, is it in here? Handshake timeout. No. Handshake message. CD P2P back handshake message. In peer.go. So handshake message is 0 times 0, 0. And I reckon that's going to be in here somewhere. Framing. Nah. So the code that's put onto, in a message you get a code and the actual byte stuff. The handshake message is 0, so the first message that's sent over is a 0. Nothing. And this R, which is proto handshake, which I don't know yet. We'll find that in a little bit, hopefully. So that gets sent over the read write. And then Go function set concurrently. The error comes back in here. If there is an error, no, if you read the protocol handshake, cool. So you've sent the handshake message, you then read the response. Into there. Whatever there is, there's an R and a there. If there's an error, we return nil as there, an error. And I don't know what there is, but there's a proto handshake. R protocol handshake, there protocol handshake. Take ours, theirs. This is obviously going to come up pretty soon. Does have a version though. Read protocol handshake. We've got a message reader. And all it does is literally calls read message on it. If the message.code calls disk message, disconnect before the protocol is valid according to the so the code 0 means handshake, 1 means disconnect. Var reason equals disconnect reason. Where do they get disconnect reason from? You decode the payload and the reason. Message.code equals disk message. Disk reason. Peer error. Underscore error. Disk reason. So that's just an integer. And if the integer, the first one, is a disconnect network error. So it sets it as a network error, decodes the payload in the message and says it's a, and then passes back reason. Zero. Cool. again, digging into this handshake a lot, but handshake message, expected handshake got error code. Proto handshake, return. Cool. If this is an error, if the code does not equal 0, expected handshake got a different one, like a Pong or something, I guess. Is that what the other one was looking for? So proto handshake structure, haven't seen that yet. They decode the message into this structure because it's RLP encoded, going to be decoded into that. If the ID does not equal 64, return invalid identity. Otherwise, you actually pass back this proto handshake structure. The point of this is it does a handshake. Here it makes a handshake. You read their response, and it gives you the handshake response, which I imagine is just a message encoded into a nice structure to deal with the handshake, because the handshake is quite a big chunk of all this file. Do encoded handshake takes a private key and a public key. So you got your secrets, and this is what's trying to establish. The handshake's trying to build this secrets. Secrets represent the structure, so it's actually in this file, so we'll go down. Really close, 206, 10 lines. Enc handshake secrets. Do enc handshake. This contains the state of the handshake, who's the initiator, who's the remote, private key, public key, remote, random, public. Cool. So receive encoded handshake if dial equals nil. PRV. What's PRV? Receiver enc handshake, initiator enc handshake. So this is just saying that you can either be the person sending it or receiving it, and you call this with your private key, and if there's a connection you use that. Creates a new frame with the secrets. Yep, cool. So does the handshake here, and if it's successful, it'll create this frame which now you can write and read to, which is your underlying communication structure. Cool. So that helps a little bit. We'll ignore the receiver enc handshake and initiator handshake. To get into them, because I imagine they're doing something similar to this. So you got an rlpx. When it's first created, all it's got is a dial, like a connection, and then does the handshake. The result of the handshake gives you this secrets, just get a little bit down. And then it puts those secrets and the file descriptor for where you write it into this new frame, which makes this read-write frame, which going onwards, when you have rlpx, you can do write and send and receive, whatever. Enc handshake, secrets. So you got the person you're talking to, MAC addresses. So these are just the signatures, I guess. And this is the token. So this is the actual secret, which is used to encode everything. And that's what's negotiated during the handshake. Cool. Authenticated message v4. Authenticated message response. I think what adds more to this fun stuff as well is there's several different versions, so they're all doing the same thing. So you got an encoded handshake. It's called after the handshake is complete. Enc handshake. So this enc handshake structure is what they're building at the very start. But it's different to this proto handshake. Don't know why yet. Who knows? So this enc handshake, after you've done it, you call secrets, and it builds the secrets and returns it. And the secrets is okay. Crypto magic, really. They're doing hashes using the public keys. And that's about as much as I'm willing to delve into crypto. The underlying magic of crypto is crypto, unfortunately. This isn't even part of it. This is put a transport protocol. So they shake hands, make some secrets, save those secrets, and that's used to encode it. I think I'm more interested in trying to find how messages are sent as after this has all been done, because I imagine you just call, here is my node that I want to talk to, do a handshake with them, they return a successful handshake, and now you've got a connection you can send information over to. Static shared secret returns the static shared secret, the result of a key between the local and remote static nodes. Takes a private key. So you got the private key. You take their, what I imagine is their remote address, which is a crypto hash, and that is generating a secret. Whatever h.remote is. Let's go back up here and have a look at it. It's a public key. So more crypto. Initiator encode handshake. Negotiates a session token. Secrets. It should be called on the dial-in side of connection. Local client's private key. See, this to me seems like they got 3 or 4 versions of like a proto encode handshake and an encode handshake. So they're doing these authentication messages, formatting them according to these authentication protocol structures, where you put the remote public key, the shared secret you want to have with a nonce, and then once the handshake is completed, you get your ephemeral shared secret. So you've got your private key and the remote's public key. Cool. So it looks like they're combining your private key with the remote's public key. Gives you one of the shared secrets which you send, and then they do something similar, and then you combine them to get your shared secrets. So skip all these handling authenticated responses, encoded handshakes, handle authenticated message, so this is a function that can, if you are a server and someone sends you an authentication message, it will call this function with the message and the local's private key. Then it gets the public key out, gets the nonce from it. So it sets the nonce, sets the remote. Generates a random key, just a random number. Check the signature. Token. Header shared static secret. So it gets this shared secret into this token. It XORs together the token and the nonce. And it just returns an error. So this handshake file structure, you would get a message coming to your server. It would tick off an event that says you should handle this message coming in. You check that it's a there's an authentication message. You create this new encoded handshake file and you start building that. And you start building that by calling this handle message function. Handshake, handle, authenticated response. Or you can make one, depends if you're the one sending it or receiving it. Using this. You got an empty one, call as make. Generates a random initiator nonce. So that's random, sets a random nonce. Random number just to encrypt it with. You sign the message. You XOR the token, and that gives you a signature. You sign, signed. You make a new authenticated message, which is going to be our message structure wrapped in another authenticated message structure, which I'm assuming it might actually be in here. But yeah, you got your blank structures, and you build it up. Ooh, wait, this first one. This makes a new authenticated message, makes a new encoded handshake file. Then you call the handle authenticate message with the actual message. So you're given a connection. You read, you make a new blank message, and you read into the blank message from this connection the auth packet. If you don't get any errors, ignore it. You make a new handshake, then you call this handshake that handles authenticated message, and you pass this authenticated message into it. What this auth packet does, because you read it into the auth message, and the handle auth message takes that message, and now you've got an encoded handshake structure. You make the response, make authenticated response. So they've sent you a hello, I'd like to connect with you. You respond back saying hello, yes, I would also like to respond back to you. Authenticated response message. You've got the packet got plain. So you take the authenticated message dot got plain. Authenticated response packet equals authenticated response message dot seal plain H. H is the handshake, so you seal the handshake. And that's got all the secrets. But you build in this response message. So you make it, this doesn't have anything that's signed in it here. Then you actually sign it using this handshake structure, and it makes the packet that you can actually send. The differentiating between got plain and this EIP8. So I don't know what EIP8 is, but they keep referring to it here. For compatibility requirements for the wire protocol, should ignore the version number of hello packets. When sending a hello packet, the version element should be set to the highest dev version provided. Okay, yeah, I do remember them talking about it a little bit. If you've got this protocol and it refuses everything because it only accepts, they just upgraded it so it can view newer versions. Yeah, okay, cool. What do they do? Yep. Seal EIP or not. So there's two versions of it because they updated it. Then you write the authenticated packet to the connection. And the connection where's the connection come from? Oh, it's just a read writer. And you return the secrets. So you actually send the message, you return your secrets using that packet and the response. Handle authentication message is what we're looking at before. You've got your handshake file, which is made in this receiver encode handshake. Okay, cool. Doing more handshake stuff, make authenticated response. And if I remember correctly, this one doesn't actually do anything with signatures yet, it just makes the message. So it's got a random nonce. Makes a new message, authentication message, copies the random nonce into the message, so it sets it for the handshake, sets the message version for, I reckon that message version is in here, ACK version 4, to comply with this new forward upgradable transport structure. Seal plain, this will actually take the message and put the signature into it using the details in encoded handshake, I imagine. Authenticated message length, that's a constant defined at the top, I imagine. Copy the signature into N, put the public key into N. So N is then building the actual thing. So it's got the signature, which I thought they were making. Okay, so the signature's already there. The hash of the public key and private key. The initiator's public key and this random nonce. Then they encrypt it using the remote's client, the one that you're talking to. You're using their remote public key. Put it into this reader. You put the buffer. So what you've put in the buffer is buffer n. So this is returning the size. So they're copying into the buffer, copying into the buffer, copying the buffer. This has got the size. Set the last one to 0. Encrypt that buffer, and that returns a byte array that's used up here, and that's what's actually sent over the wire. Decode plain, seal plain. They're all doing the same thing really. Seal. They're just decoding and doing the handshakes. Which they start here, they make a buffer. Seal ERP8. They got a message. You got to encode the message into the buffer. Pad it with a random amount of data. Then you encrypt it. Then you append the prefix, which is a 2. That's the difference between the signature and ERP8. The other one is they put a prefix of 2 and then they pad the data a random amount of length. Cool. Don't understand why. Read handshake message. The opposite, you got a message now. Import public key. Returns a public key or an error. So the public key is a 52-bit public key. Length of public key. So this just takes your byte array, puts it into a public key. So when it's saved, crypto unmarshaled public key. And here's Azure. So they define themselves. How do they do that? They go through 2 byte arrays, 1 by 1, and if they are equal. Very efficient. So that is the end of all the handshaking stuff, which is slightly boring because it's really technically deep, and it's like stuff you don't really want to mess with unless you know it, which is you've studied for a very long time. And then here they actually start where you can talk over it. And this is probably more where I want to look at today. 0 header 016. So this frame has the connection, which is what actually gets written to. And then it's encrypting it and decrypting it as it goes, and it's updating this signature as it goes. So they make a new frame, taking the secrets, so you've already established the secrets. So you take the MAC address out, the AES out of the secrets, which are crypto magic really, making new ciphers out of them. And then cipher, new CTR, encoding IV. And then they save it into this frame, pass the connection. So when it does a read or a write, it'll pass it through this cipher using the secrets that are already here, and it will then pump it through this connection, I imagine. So the write message, you've done the handshakes, you're now going to send a message, which might be the Ethereum protocol, or it might be a Swarm message where you're transferring file data, or it could be Whisper where you're actually sending messages to other people, human readable messages. So you got the message structured as a message, and in that encoded, they encode the code. If the snappy is enabled, I don't know what snappy is. I think it's a version. Where they don't check so much. Ethereum snappy. Snappy Ethereum. I don't think this is it actually. Nothing as snappy Ubuntu. I think it's just where they communicate. And they delete some of the important information out of these to make it quicker, I would imagine. Not delete. Snappy compression algorithm. Compression algorithm. So no, actually it's got, sometimes a message will be, you can compress the message. Interesting. Okay, cool. So instead of just sending a raw byte array of the RLP, they actually compress it before they send it. And that is just a snappy dot encode. Puts it into a payload, then sends a message.payload. Then make a blank header, and the header adds a message.size to the p type. So p type is just the code encoded as RLP. So whatever the code plus the message size equals the file size, and if it's bigger than 24 inch, yeah, blah. So they copied the 0 header into everything after the first 3. Because I imagine all those checking and stuff is actually only the first 3 bytes. Because I would imagine that this is just 1 byte, and the message.size would be 2 bytes. So they chuck a 0 header, which is going to be a constant, and they're just going to, at the top somewhere, I've built it. And a XOR keystring. So you encode everything up to the first 16, and then you write the header MAC, which is everything after the 16, and that is then finally head buff. Message.payload. So there's updating the message payload. Egress math. So they're encoding the first stuff, which is boilerplate boringness. They're updating the signatures for the first 16 bytes, which are just the encrypted nothingness. Then they write that over the connection. And then, I guess this is where they actually encrypt the message, so the message payload. So T equals cipher stream writer, secrets the writer. And then if you try to write the code to it, it gives you an error. So they have the stream, write the code to it, blah. If that fails, return the error, which hopefully shouldn't. Then they copy into it the payload, which is going to encode it. So that's an error, it's blah. And then they put some padding. So they got this T cipher. That they've written into. Egress MAC hash is up to date because the frame content was written to it as well. Cool, so it's all in here. If they write so this cipher.streamWriter takes the connection where we're writing directly to the connection, the header. And then the payload is written to via a cipher library. And that makes some sense. So this header is formatted specifically. And then the actual payload is written. Cool. And then they're updating the signature. At least I believe it's signature. Crypto Mac. So, message authentication code. Yeah, it's a signature. A signature is specific to signing a message when it's a communication. It's this. Cool. So, update the signature, message authentication code. And then they write that to the connection as well. And I guess read message is the opposite. You're returning a message. So you got your header buffer, IO read full from the connection into header buff. So this is a 32 byte buffer. You're reading the first 32 bytes into it from the connection. If there's an error, you're returning nil and the error. You have to verify the message authentication code, which is doing a reverse because there's an authentication code coming in, authentication code going out. So you're making sure that they should equal what's in the header. Blah, 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 making sure that that all matches up. So this is more crypto magic. They're just checking that the headers in the transportation frame are legit. You know, if not, it's a bad header. And they don't look into why, but whatever reason. Now they ignore the protocol type. That's them saying the ERP8 we were looking at, where they don't look at the protocol type. Then you actually read the frame content. Frame size rounded up to 16 byte boundary, so it's a padding. So you read into the frame buffer. That's this frame buffer, which is R size. So you take the file size, or the frame size, is rounded up to, so that's a constant. So where's that going to be defined? mngg, and then this is all in the right message. I want in the read message. Read message file size equals read integer 24 header buff. So they're taking it straight out of the header. So they're making this read size, and they know that it's rounded up to the 16th byte. So you take the file size mod 16, which is the remainder when you divide it by 16. And you increase it up to 16. So you're reading the rounded up size to 16. And you're making a frame buffer with that size, rounded up to 16. Going to your connection, reading it into there. However, I don't see them decoding it yet, so that's what's going to be now. So you're updating the Mac, the signature for the stuff coming in. So I guess everything that comes in, you've got a signature that gets constantly updated, and everything that gets sent is the same. And then the peer on the other side has the equivalent, but just reversed. So the ingress becomes the outgress, egress. If there are, so they're reading the ingress, which was the egress of the send. So up here, the last thing it was write the egress to the last little bit on the frame, and that gets read here into the ingress, and then you check that everything you've gotten so far matches what that guy has sent. And if it doesn't, then you spit an error, you got a bad Mac. If that's all good, you decode the frame buffer using this XOR keystring, which is this DEC on this RW. Don't know what that means yet. But there's an inc as well. So somewhere there's an inc and a dec. Increment, encode, decode. And then they put that frame buffer into some bytes. Recursive length prefix, they decode those bytes and the message code. Build the size, build the payload. The message is in the parameters that are set here. And if Snappy is enabled, you've got to decompress the message. So they're doing quite a lot. So they're reading 3 stages out of it. They're sending us 3 stages. They're sending a header, they're sending the actual connection payload, and then they're sending the Mac. And then they get given this frame buffer, which is encrypted. They decrypt it here. Decrypt from frame buffer into frame buffer. Pulling that frame buffer into an array of bytes, which is the recursive length prefix encoding. And then if it's compressed, they decompress it. Cool. Update Mac resets the given hash. So you got the hash, you got a block, and you got a seed. Crypto magic, you're encrypting the buffer with the Mac. So you've got a hash, and you've got a buffer. And taking this block, you got a cipher block, which is going to be why it was 16 bytes, because the cipher has to be rounded to 16. And then that gets encrypted according to the MAC, which is the hash. So when they're writing here, okay, cool. So you got the MAC address, and you got your cipher, and you got your seed, which is sum at nil. So then you use that MAC to encrypt that, and that gives you the new MAC, which gets written into this, and they update it. Cool, that makes sense. You encrypt it, go through every item to the power of the seed. It's more crypto magic, really. The result is you've got some array of bytes. You've got a magic number, times in these by this magic number, and it gives you another magic number. That magic number has certain properties, and that it'll always be consistent if the same numbers are going in. This is based on secret information that you transferred at the start. This is encoded, so it ideally means that no one else can copy it. Now I kind of want to know what this encode and decode stuff is. rw.dc. rlpx frame rw. Cipher.stream. So there's going to be an encode and a decode here somewhere. Cipher.stream represents a stream cipher. It XORs each byte with the key stream. Destination and source must overlap entirely or not at all. So I can't really see where this encrypt they call the XOR key stream. On it. Stream.XOR keystring can now work in place. So all these must be interfaces to another library or something where you can write by XORing a MAC address authentication code against a byte array. Cool. So that's all that is. So really, where are we? P2P. Yeah. So we had a look at yesterday at the message, and that really was just a byte array with an integer, which is the code. We've kind of seen today that the code turns out to be 0 if it's a handshake, 1 if it's a failed, declined, disconnected. Then it's got 2 if it's a ping message, 3 if it's a pong message, and then I imagine everything else is completely haven't seen yet. So the messages are sent using rlpx, and they've got underlying everything this lpx. Starts off with just a wrapper around this rlpx frame read write. rlpx frame read write. Which has got this connection. And when you make this new connection, so you go new rlpx frame, you pass in the TFD. So when they're making that, they're passing this net.connection, and that is you can dial a IP address with a port, and you can write to it the same way you write to a file, exactly the same. In this case, he's written get in capital letters space HTTP, which is literally just a get. If you send that to a HTTP server, so something that holds web pages, it'll actually give you back the website. That might be good to do right now, actually. See, cd tests vim main net. And if we go so this is a connection. Sudo net.dial TCP Golang. You write to that connection, and you status read string. If we do go run main undefined buff.io. Is that it, right? What is it? sends an OK message back. So how do we get it out then? So they've got this connection, and you just write to it. And in here, they've made the connection already. That's external. Haven't figured out where that is yet. I imagine it's in one of the peer or the server files. And then when they want to send messages, they literally just write straight to it with their encrypted magic they've done. And this is the protocol is entirely defining how that encrypted magic is done. But if I go read, make authenticated message. New reader. Maybe I could do it that way. We'll do exactly what they've written here. Head buff. So they've got I was going to say 32. They get a frame buff here equals make byte 32. It's not 32. And they do that. If that slash error does not equal io.read full the connection, which is con, and into frame buff the error does not equal nil, panic error. So they've written to that connection, you made a connection, you're expecting a reply. IO read full, what does that return? Read string? No, read full. Oh, that's a bit scary. Make buffer read full into R. I think if we just go this probably needs to go away. Cool. So all it sends back is the date. No, it sends back everything. Where was that? Cipher. Net. If we select just that, copy, go into here. That redirected it. Cool. So that was everything that sent back. So I don't know where they're making that connection yet. rlpx. It might be in vim rlpx.go. New rlpx test server. So in the tests. But in server they do something. Where's that? 47. No, 431. If the server transport equals nil, new rlpx. So you start your server, you now can listen to people. Then they got this new transport equals new rlpx. But that's just a function. So there's a server structure, has a new transport, which is a function that returns a thing. Come on, where are you? Here we go. Yeah, okay, cool. So you got new transport, which is just a function that takes a connection. I want to know what this new transport is called. Next. Set up connection. File descriptor. Here we go. So it's passed up again. So server, you call set up connection and you pass FD. And this is external to it. And attempts to add the connection as a peer. It returns when the connection has been added as a peer or if it's failed. So where does set up con in this one? Listen loop. So the server calls setup connection FFD. New metered connection FD. I don't know what new metered connection is. Server dial metrics. Still, where'd that FD come from? Because they're just passing it through anyway. FD equals remote address. So they make a blank connection here. So on the loop, this is just listening for people to connect to you. Slots. Number of tokens equals default max pending peers, which I believe is 100. Default max 50. Completely wrong. So you make a channel, because obviously when a connection is made to you, you spawn off a new process. Server loops slots equals that for all the tokens. This is concurrency stuff. So serve.listener.accept. So in here, they get a listener, net.listener. What is that? Generic network listener. So that's just the net. So you've got that. And then you've defined the listener here, which is this net interface. And it has a list of people who have sent stuff to you. So people are sending to you the requests for to connect as peers to you. So you sit here and this gets spawned off in another process, so it doesn't block the main Geth, and it just does a for loop. And as long as there's a slot where you can put it, listener.accept. Now is that blocking? Accepts, waits for, and returns. This waits for a connection. So here, go back. You got your listen loop. You started your server, you're listening, you're waiting for connections. And all they are is these net files that people are writing to, and you're on the other side, on a different side of the world, to receive them. Someone's written something to you, and you're running this listening loop, and this just does an infinite loop over here. But this blocks it, so it says listener.accept, and nothing happens if no one tries to connect to you. So this process sits in here and waits, and once it does, you get this FD, which is this connection you can play with. And then, if you got errors, it spits it out at you. And then it breaks out of it, because it's got this FD file descriptor. Restrict if it does not match net restrict. Not whitelisted in net restrict. It says a whitelist. I don't know why that's there or what's coming from at this point, but checks that that connection is not a whitelist. Probably because they got spammed, something shocking for a while. New net internet protocol. The remote address, so they get the TCP address out of this FD. Net.connection. So where's this connection one again? I want to know the structure, what's in it. Con is an interface that has a read, a write, and a close local deadlines. So you got a connection. It's got a local address and a remote address. Cool. So that remote address, they're just forcing into a TCP address. So you got that saved there, which would just be that actually gets saved into the ID of it, I believe. CD params vim boot. So it'd be like, it just returns that. So you got that remote address. What is that? That's an address. What's an address? It's two strings. A network, TCP, and the network string. Cool. So you got that returned as a string. What do they do with it? They're checking if it's in there. Net restrict, whatever that whitelist they're doing with it is. Oh, they're doing it twice. They do it in this. IP equals TCP IP. Cool. New metered connection does something with it. Don't know yet. It's in metrics, I believe. See, peer-to-peer. Vim metrics. So they make a new metered connection. Which is just extending network connection. Is a wrapper around the connection that meters both inbound and outbound. So it's a metered connection. Checks how much that person is sending and receiving. I believe it's because they got so much spam and shit. So they're just extending the network connection to give it some extra stuff and make it be traced. right into the thing saying you accepted a connection, and then you're calling this server setup connection with this connection, which goes to setup connection right below it apparently, and that is where we create a new connection object. And that connection object is passed to this other one. So down here, you've now got the connection. Someone's tried to connect to you. Set up the lock, get the public keys from where? Flags. Dial destination enode. Dial dest. Where'd dial dest come from? No, it comes as a parameter. Set up connection with nil. So it's passed as a nil. They pass nil, nil, nil. Dial dest does not equal nil. They'll do stuff. If it does, like it's ignored because you actually have the destination. You got the connection, do encrypted handshake. So this is where it's actually, now someone's tried to connect to you, you're doing all the handshake stuff that we were looking at just before. If you failed RXP, node from connection. If it does passfully get a successful handshake, they add it as a node. What's C in this case again? The connection. The handshake is done. Login is going on. Run the protocol handshake. Do proto handshake. Ooh, so this might be do run the encryption handshake, then you run the protocol handshake. So first step is encryption, then you do a protocol handshake. I don't fully understand what was going on with those because I kind of glossed over them, but handshakey stuff. Checking that you got a successful connection with them. If checks successfully completed, run peer has now been launched by run. Do protocol handshake. Cool. Run peer. Runs in its own Go routine. So the handshake, when it's done, calls this run peer. And you send peer event. Don't know what a peer event is. Saying, hey, look, I want to add you as a peer. The peer event is where you synchronize with them if it's someone's out of out of sync with their blockchain, I believe. Run peer. And this isn't here. This is going to be in the other one. Cool, I might call it there for today. So what we looked at is we've gone through this rlpx transport net protocol. There's a lot surrounding the handshake, but in the end all they really have is this net connection, which is the same as when you're got a web server and you make a request to a web server and they send stuff back to you. Exactly the same. You send a header, you send the frame data, and you follow it up with this new MAC. And those items, this is consistently updated, and that's what encodes the frame data. And that's just encrypting it. We saw that they've got a little bit of compression with the snappy after it's been saved as a RLP byte array. So I think that'll be what we look at next, probably tomorrow, is this RLP, not the transport protocol, but the actual way it's saved. Because it keeps coming up, as everything is saved as a byte array, which is them instead of using JSON or something because it's smaller. And I guess everything over a network is about size. Anyway, thanks for tuning in. Catch you tomorrow.